of a exponential function is y equals c to the x. Well, now we're going to start to apply transformations to it, so stretches and reflections and translations. So similar to our transformations unit, if we multiply this entire function by an a, this is going to represent our vertical stretch by a factor of a. If we multiply just the x value by a b value, this is our horizontal stretch by a factor of 1 over b. If I apply a horizontal translation, that would be applied just to the x value, so that's going to occur in the exponent value, and that's going to move the graph left or right. And then our k value, if I add some value to the entire function, this is going to translate the graph vertically. So we're just going to quickly take, given the original function y equals 2 to the power of x, we're just going to look at each of these functions and describe each of the transformations. So starting with y equals 2 to the x, if I've multiplied the entire function by a negative 3, well, the 3 tells me that there is a vertical stretch by a factor of 3. And the negative tells me there is a reflection in the x-axis. So our transformations are really no different with exponential than any other transformations we've worked with. Question B, 2 to the power of negative 2x plus 6. So before we talk about this horizontal translation, remember this b value always needs to be factored out of this expression before we can talk about our translation because of our order of operations or order of transformations. So in my exponent, I'm going to factor out a negative 2 first, and I'm left with the following function. So now my b value is 2, so this tells me there is a horizontal stretch by a factor of, and remember we need to reciprocate our b value, so it's a stretch of 1/2. The negative tells me there is a reflection in the y-axis. And then this h value, x minus 3, tells me that the h value is a positive, so there is a horizontal translation of 3 units to the right. Okay. And then lastly, given the following function, y plus 2 is equal to 1/3 times 2 to the x plus 1. Well, before I talk about my transformations, I'm going to solve my equation for y. And now we can talk about the transformations. So our a value is 1/3, so this tells me there is a vertical stretch by a factor of 1/3. This tells me that there's a horizontal translation of 1 unit left. And this tells me there is a vertical translation of 2 units down. Okay, so that again is another review on transformations. All right, moving on. Given the following equations of the functions, we are going to match each graph below to its correct function. Okay, so key things that we want to look for is the change in our horizontal asymptote. And normally with our function y equals just c to the power of x, our horizontal asymptote would always be the x-axis. Well, we have to think about, well, what's going to change that? What value will change the horizontal axis? And that is the movement of moving the graph physically up or down, which is our k value. So the horizontal asymptote actually is represented by the k value. So that's the first thing I'm going to look for is what is my new horizontal asymptote, and if I still have horizontal asymptotes that are the same, then I'm going to look for translate or horizontal translations, and then I'm also going to look for stretches. But the first thing we want to look for is where has that horizontal asymptote changed to. So for question A, if my k value is a -2, this tells me that the graph has moved down 2 units, which tells me my new horizontal asymptote will occur at y equals -2, which is this graph here. So function A relates to the first graph, so this would be A. Question B, we can see that our horizontal asymptote is at a +1, which is represented by this graph here. So this would be graph B. And I'm also going to take a look at, well, my constant is at 2, which would normally give me a exponential growth, but because the graph is being reflected in the x-axis, it should now create a exponential decay, which is the shape that I'm getting here a little bit. Here, question C has a horizontal asymptote at +2, which is here, so this would represent match to C. And then here, there is no k value at all, so my horizontal asymptote should be the x-axis, which it is. So this should be D. Okay. All right, moving on to example 3. Given the function 6 times 0.75 to the -x plus 2, determine the following characteristics. Okay, so if we can imagine our original function. So our original function would be y equals 0.75 to the power of x. So this is our base function. We know is going to be an exponential decay, which looks like this. My horizontal asymptote would be at the x-axis. This y-intercept is at 1. Okay, so let's try to visualize what our new function is going to look like. So if I were to sketch my new function, I know that my horizontal asymptote is now going to occur at a +2. This has been vertically stretched by 6, so technically this y-intercept should now be at 6 instead of 1. And then it's also being reflected in the y-axis. So it's going to be reflected horizontally. Okay, so what was originally this way is now going to go here, but then I'm going to reciprocate it or reflect it in the y-axis. So my new graph should look something like this, where this y-intercept was at 6, but I'm also moving that up 2 units, so this is now going to be at 8, right? Because I vertically stretched it by 6, so that y-intercept becomes 6. I'm reflecting it horizontally, which isn't going to affect that point. Then I'm lastly going to move everything up 2 units, so this y-intercept should now occur at 8. Okay, so what is the domain of my function? Well, the domain of my function really hasn't changed, so it's still going to be all real numbers. The range of my function, that has definitely changed. And your range is directly related to this k value. So my range is going to be everything greater than 2. So it can't be equal to 2 because that's our asymptote, where y belongs to the reals. Our horizontal asymptote should be equation of y equals 2. And our y-intercept, we've already talked about it, was originally 0, 1, and then we vertical stretch by 6, So this would become 0.6. And then we want to apply vertical translation of 2 up, which leaves us with 0.8 would be our y-intercept. Okay. All right, moving on. So that was all transformations. We're now going to move on to some new vocabulary. We're going to talk about compound interest. Okay. So compound interest is interest earned on an investment and is returned to the principal to accumulate with it. So, for example, if an initial investment of $500 is earning $6,000 per year, or often we would see this per A for annum, this A really represents that's the interest rate per year. And it's compounded monthly. Show how the investments grow, how the investment grows over the first 6 months. So when you think about compound interest, if it's compounding monthly, then what is happening to your money is that the interest is being applied to the $500, but it's not being applied to it every year, it's going to be applied to it every month. But the interest rate given is always a yearly rate. We always want to change that to, in this case, a monthly rate. So the first thing that we'd have to do to this interest rate is, because we're compounding our money monthly, we'd want to take 6% and divide it by the number of months per year, which gives us 0.5% per month. And then you'd want to change that to a decimal to apply that value to our money. So if we started with $500 and we wanted to figure out how much interest we earned in the first month, we'd go $500 times the interest we're earning per month, not per year, but per month, and multiply those values, and we get $2.50. So what happens with compound interest is that this interest gets added to the principal, and then the next month we're taking this new accumulated amount and we're finding the interest earned on this amount of money as opposed to the original $500. So now we're going to take $502.50 times that monthly interest rate again. So in this second month we're earning just a little bit more interest, which is $2.51, which gives us a grand total of 505.01. We're going to take that amount of money, multiply it by the monthly interest rate again. And as you can see, over time, the interest that we're earning on this money is a little bit greater each time because our principal is increasing by this interest amount. Okay, so over time, so that is how compound interest works. Every time your interest is being calculated, that amount is being added to your total, and then your new interest is calculated on that new total. Okay, and so this just shows you how much money you would accumulate over time if it was over a 6-month period. Okay. All right, so how do we generally use a compound interest formula? So this formula is on your formula sheet. Y equals A times B to the power of X. Okay, where Y would represent the accumulated amount that you are getting. A represents your principal amount, how much you're starting with, so that's your initial amount. And then your B value represents your interest rate. Well, your interest rate has to be the interest rate per the compounding period, not your annual interest rate. Okay? So, and if our interest rate is 0.015 or 0.005, we always need to add a 1 to that so that it's actually calculating the interest rate, but the 1 is going to actually add it to the initial amount that we started with. Okay, so it needs to be a 1 in front. And then X is the total number of compounding periods. So in this case, if we were to try to find this total, rather than calculating this every single month, but wanting to figure out this total over a 6-month period, I would take my formula and go 500, which is my initial amount. I'd multiply this by 1.005 because this is my interest rate per compounding period, so per month. And then I would take this to the power of 6 because that's the total number of compounding periods that are occurring. So I'm compounding this 6 times. So on your calculator, if I went 500 times 1.005 to the power of 6, 500 times 1.005 to the power of 6. We get the same amount that we did in our chart, $515.19. Okay, so this is just a quicker form in order to get this grand total rather than having to create this chart. Okay, so your money can be compounded at many different rates in a year. The most common one is compounded monthly, but that is not with all money. For example, credit cards, they whenever they start to charge you interest, they charge you interest compounded daily. So they're charging you interest every day until you actually pay your credit card back, which can be quite expensive. So compounding period, the time over which interest is calculated and paid on an investment or a loan, the interest is returned to the investor at this time. So for example, if your compounding period was daily, then you'd want to take your annual interest rate and divide it by the number of days in a year, 365. If your interest was being compounded weekly, then we want to divide it by 52. Semi-monthly, which is twice a month, would be annual divided by 24. Monthly is probably the most common, 12 times a year. Quarterly, right, that would be every 3 months, which is 4 times a year. Semi-annually, twice a year, and then annually would just be once a year. So just remember that your B value in the formula must be divided by the compounding period, then added to 1. So remember, your B value is not the annual interest rate, it's the interest rate per compounding period. And then your X value isn't necessarily the number of years, it's the number of years times the number of compounding periods in a year. Okay? All right, so we're going to go through just a couple examples of compound interest. So it says Amy invested $5,000 in an account that pays 6% per annum compounded monthly. How much did it appreciate to after 4 years? Okay, so when I think of this question, my principal amount, which is our A value, is $5,000. Okay, my interest rate is 6%. So my B value is I want to take 6% and I need to divide that by 12, which gives me 0.005, which is 0.5%. So that tells me my B value is going to be 1.005. Okay, I'm going to change this to a decimal now by dividing it by 100, and then I always need to add 1 to that for my B value. And then my X value is going to be, well, I'm investing this money every month, so that's 12 times a year, times 4 years. So my money's actually being compounded 48 times in this time frame. So my accumulated amount would be Y equals 5,000 times 1.005 to the power of 48. So I'm going to go on my calculator now, 5,000 times 1.005 to the power of 48. So her money has accumulated to $6,352.45. Okay. All right, and then the last example, Christine invested $2,500 for 4 years compounded semi-annually and received $843.26 in interest. What was the annual rate of interest? All right, so in order to, basically what we're trying to find here is our B value. This is what we're looking for. And it's an annual rate, okay? Our X value is going to be 4 years and it's compounded semi-annually. So we're going to go 4 times 2, which is 8. Our A value, that's our principal. She initially invested $2,500. And then we know the Y value. Now remember, the Y value is the total accumulated amount. It's not just the interest amount. So I'm going to have to take my principal plus the interest that I earned. Which gives me $3,343.26. All right, so now I'm ready to calculate for my B value. So I'm going to input my Y value is 3346.26 equals my A value is 2,500. My B value is what I'm looking for, and this is going to be to the power of 8. All right, so to solve for B, my first step would be I'm going to divide both sides by 2,500. And we're going to try and leave this value inside our calculator. So I'm going to leave that on my calculator. So 3.34 approximately on my paper is equal to B to the power of 8. So now, in order to solve for B, I want to do the opposite operation of taking this exponent to the power of 8, which would be the 8th root of 1.33734. So I'm going to go into my math. Sorry, I got to type in 8 first and then hit math, number 5. So I'm taking the 8th root of this previous answer. So I get 1.037 for my B value. All right, so remember my B value. First of all, the 1 is something that we'd add, so we'd want to subtract 1 from that. So now our interest rate would be 0.037. Multiply that by 100 is 3.7%. But remember, this would be per semi-annual. This is the semi-annual rate. So what I need to do is I need to multiply, because a semi-annual is twice per year, I'm now going to multiply that by 2 to get my annual interest rate, which is 7.4% per annum. Okay, so when you're going through this, remember that B value, right, is relates to the interest rate per compounding period. This is not the actual annual interest rate. So things to keep in mind.